Welcome. In this video I'm going to show you how you can perform a one sample trimmed mean test, or sometimes referred to as a Yuen or Yuen-Welch test, with Python and not using any libraries. Now this test is usually done with independent samples, but it can actually also be done with a one sample scenario. I'm using Jupyter Lab with Python version 3.818. This test can be used to test for a single mean. So I can set, for example, that I expect the average age to be 50. And is similar therefore as a student t-test, but instead it uses not the regular mean, but the trimmed mean and a winterized variance. There are actually two variations for the calculations in the standard error, so we're going to go over both of these. To load some example data, I'll import pandas. And then I'll have a file called GSS 2012 containing the general social survey data from 2012, slightly adjusted for example purposes. Oh, shouldn't change the link. I'm going to read all of that. It's a big file with, well, big, relatively term, with loads of fields actually, but I only need one numeric field. So age seems to fit the bill, but actually there's an 89 or older category. So I'm going to replace that with 89. And also make sure everything is numeric. So that's what this little bit of code does, and I store all my data as scale fields. So this now has just only the ages as numbers. I'm going to set my hypothesized mean to 50, and that will get us started. Now in another video I'll show you how you can use my own library to actually perform this test quite quickly, which means it runs everything. But if you don't want to use any libraries, we'll have to do it the hard way, because I'm not familiar with any other libraries in Python that can actually do this test. So we're going to create this formula, which is the average with a t, which is then the trimmed average, minus the hypothesized one divided by the standard error. And this standard error is usually the standard deviation divided by the square root of n. So in essence, what we can do is simply take the sample size, which is the length, and then let's say we want to trim from each side 5%, so 0.05. Then the number of scores that I want to trim is actually the lower, rounded to the nearest integer, well actually lower integer. So n times that percentage, and that gives me, I call it just a g value, so I need to actually have 98 values. This also reduces the sample size, so from each side. We're actually going to do this twice, so that leaves us with then 1773 scores. Now the trimmed mean is all of those that are not trimmed divided by how many we have actually trimmed. So I'm going to call the sorted data as yi instead of xy, so that's simply x sorted. And then from the first one that's not trimmed to the last one that's not trimmed, we sum all of those scores and divide it by how many we have. So I can simply use the sorted function and then sum the specific range and divide it by those that 1773. We actually also need the winterized mean. The winterized mean is similar like the trimmed mean. However, now we don't just ignore the values. We're actually replacing the values that we want to trim with the nearest non-trimmed value. So we can call that a winterized mean. Here's the formula for that, and that's about 48. Then we can calculate the winterized variance, as it were, or actually just the sum of square deviations, by using this formula. It's basically the average squared difference with, well, the sum of all square differences with the winterized mean. And we do this for all our sorted values, so that gives us that one. Now the standard error is actually slightly different. So Yuen actually proposed, or actually a variation, it was I think it was 2K and McLaughlin who actually came up with this. They came up with this formula. which is fairly straightforward for the standard error, while Wilcox actually uses this formula. We have all of these values, we just need the square root, as we actually also needed earlier, which we can obtain by just doing something to the power of a half. That will give us the two different variations on this test. We can finally actually calculate that t statistic, and I'll simply use both of them. So here are the two results. As you might notice, it doesn't change that much. The degrees of freedom are given by the number of scores that were not trimmed, -1. So that's fairly straightforward. And then we can use the student t distribution with our t value and our degrees of freedom. I'm going to be using SciPy for that. I do have a separate video if you really don't want to use any libraries, but for these distributions, it's quite common to actually use SciPy. I can then fill out the formulas. Both of them have a e -1 -0.7, so that means I need to divide this value that's before it by 10 to the power of 7, which is extremely low. It's far below the usual threshold of 0.05, so we would reject the assumption that the population average is 50, or the average age is 50, and we have a significant difference therefore. Alright, I hope this video was helpful, and thank you for watching.